In this video, I want to talk about leaving group stability. So let's compare this compound versus this compound. And we might ask, which is a better leaving group? Is this chlorine a better leaving group, a more stable leaving group? Or is this hydroxyl a better leaving group, a more stable leaving group? Because we know these compounds can go through reactions where these guys act as leaving groups. For example, we know this chlorine can act as a leaving group, where essentially the electrons in this bond fall in the chlorine. So when the electrons in this bond fall in this chlorine, we effectively break this bond. And when we break this bond, we're left with this product, this carbocation product, and we're left with this chlorine, this chloride product. And again, the same thing can happen here where this hydroxyl acts as a leaving group, where it leaves, where this bond breaks, and these electrons fall in this hydroxyl, creating this hydroxide. However, we might ask, which set of reactions is more likely? Is this chlorine a better leaving group? Or is this hydroxyl a better leaving group? So to determine that, we need to find out, is this chloride a more stable leaving group? Or is this hydroxide a more stable leaving group? So how can we determine which is a better leaving group? Well, the way we determine this is by looking at their analogous respective acids. For example, instead of seeing this chlorine acting as a leaving group, we imagine it as an acid, where instead of an alkyl, we have a hydrogen, and then instead of the leaving group, we have the rest of the acid. So why do we do that? Well, again, now we can compare hydrochloric acid to water, and we see which one is a stronger acid. Because again, we know when these act as acids, for example, when hydrochloric acid acts as an acid, what's going on? We know some compound gets protonated, stealing this proton, and essentially when it steals this proton, we know this bond breaks where these electrons fall in the chlorine, creating these products, whatever got protonated, and this conjugate base. So therefore, when hydrochloric acid acts as an acid, this chlorine is really acting as a leaving group. It's acting as a leaving group where something gets protonated and then this bond breaks and these electrons fall in this chlorine, creating this chloride conjugate base. So when this acts as an acid, this chlorine is really acting as a leaving group. So we've seen these leaving groups before. These electrons essentially fall, creating this conjugate base, this leaving group. And the same thing with this water. When this water acts as an acid, something steals this hydrogen, and then this bond breaks, and these electrons fall in this hydroxyl, creating this hydroxide conjugate base. So this reaction is very similar to this reaction. There are some differences, but again, when looking at the strength of this acid, we're really interested in the stability of this conjugate base. So when looking at the strength of this acting as a leaving group, we're looking at how stable this leaving group is. So therefore, and now comparing this acid with this acid, we can compare this leaving group with this leaving group. And we know that hydrochloric acid is a stronger acid. It has a pKa of roughly around -7, where water has a pKa of roughly around +16. And we know the lower the pKa, the stronger the acid. The higher the pKa, the weaker the acid. So now we know hydrochloric acid is a very strong acid. It's a stronger acid than water. And again, why is hydrochloric acid a stronger acid than water? Because when hydrochloric acid acts as an acid, it breaks this bond, and this chlorine essentially acts as a leaving group, creating this conjugate base. And we know this conjugate base is very stable. This conjugate base is more stable than this conjugate base, so therefore this is a stronger acid than this one. Because again, it creates a more stable conjugate base. And again, you might ask, why is chloride a more stable conjugate base than this hydroxide? Well, there are two things that create stable conjugate bases, but one thing is, again, we know we have this -1 charge delocalized over a larger atom. We know this chlorine is a relatively large atom, so that negative charge is delocalized and spread out over a larger atom. So we have a smaller charge density, which we know is stable and more energetically favorable. However, this hydroxide still has that -1 charge, but it's localized over a smaller region. This is a smaller atom, so therefore that negative charge is localized over a smaller region, so it's more charge density, so that's not stable. Having that localized charge density over a smaller region is not stable. So now we know, based on these pKa's, we know hydrochloric acid is a stronger acid than water. Why? Because chloride is a more stable conjugate base than hydroxide. So therefore, we know chloride is a better leaving group than hydroxide. Because again, it's a more stable conjugate base, and therefore this is more stable than this. So now we know chloride is a more stable leaving group than hydroxide. So therefore, this is more likely than this. So again, that's how you determine which one is a better leaving group. That's how you determine if chlorine is a better leaving group than hydroxyl. You just look at their analogous acids and see which one creates a more stable conjugate base based on the pKa's. And again, we know chloride is more stable than hydroxide, so therefore we know this chlorine is a better leaving group than this hydroxyl. And again, but however, let's look at a different example. And again, so we know, and a really important rule of thumb is that hydroxyl is not a good leaving group. That's a mortal sin in organic chemistry to see hydroxyl acting as a leaving group, creating this hydroxide leaving group. Because again, we know water wasn't a good acid. Because again, hydroxide isn't a stable conjugate base. This isn't a stable, so therefore this isn't a good leaving group. So therefore, hydroxyl is not a good leaving group. However, what if we took an hydroxyl and what if we protonated it? What if we took this hydroxyl and protonated it, creating this compound? Is this a good leaving group? Is this a good leaving group? Well, again, how do we determine if something is a good leaving group? We look at its analogous acid. Where again, what we do is instead of an alkyl group, we just add a hydrogen, and now we have the leaving group, the rest of this, and we see, is this a strong acid? We ask, is this a strong acid? And when it acts as an acid, we know we create these two things, and we create this conjugate base. And you ask, is this a strong acid? If you're asking, is this a good leaving group, you look at it as an acid and you see, is this a strong acid? And now you see it acting as an acid and you see, is this a stable conjugate base? And we know this is a pretty good acid. This has a pKa of roughly around -2, so it has a negative pKa. We know negative and small pKa, so more negative pKas is a stronger acid. So we know this is a pretty strong acid. Why is this a pretty strong acid? Because it creates a pretty stable conjugate base. And we know that based on the pKa. We have a negative pKa, so we know this is a strong acid. So now we know this creates a stable conjugate base, and therefore, so this is a pretty good leaving group. So this is a pretty good leaving group. So we know this was a pretty good leaving group. We know this was a pretty good leaving group. So therefore, this reaction is feasible. So therefore, we can go through this reaction where we create, again, this carbocation, and then again, we have this leaving group. So again, this is a pretty good leaving group because we saw it's a pretty stable conjugate base based on the pK, so we know this is a pretty good leaving group. So therefore, this is a good leaving group. So that's a really important rule in organic chemistry. Hydroxyl, bad leaving group because it creates this very unstable conjugate base and therefore unstable leaving group. However, if we protonate this hydroxyl, this is a good leaving group. This is a good leaving group because again, it creates this conjugate base which is stable, and we know this is a stable conjugate base based on the pKa. And again, so we know this is a stable, so we can create a better leaving group. And again, so one last example I want to go over is, again, let's say we had this compound. And we ask, is this a good leaving group? Is this a good leaving group? And is this likely to, again, create this leaving group? And again, we would have this. So is this likely? Is this reaction likely? Well, again, how do we determine if this is a good leaving group? Well, we just imagine it's analogous acid. We just imagine Instead of having an alkyl group, we replace it with a hydrogen, and we see, is this a strong acid? And again, if we were to look at the pKa of this acid, we would actually see a very strong acid. Again, and then something would get protonated. But we would see this has a pKa of roughly around -11, something like that, like a very negative pKa. So therefore, this is an incredibly strong acid and creates an incredibly stable conjugate base. This is a very incredibly stable conjugate base. So therefore, we know this is a good leaving group. So therefore, this is a good leaving group. So we know this is a good leaving group. So therefore, will this reaction occur? Well, actually, no. No, this will not occur. This will not act as a leaving group creating these products. Why? Because this isn't a stable carbocation. So you can't just ignore the carbocation. In this example, we did have stable carbocation, so it was okay. But in this example, this isn't a stable carbocation. This primary carbocation is not stable. So yeah, we have a stable leaving group. This is a good leaving group. However, this isn't a good carbocation, so therefore this particular sequence is not very likely. And again, why is this a good leaving group? Because again, that negative charge is delocalized over this huge atom. We know iodine is a very large atom, so that negative charge is delocalized over a larger atom, so it's very delocalized, low charge density, so that's stable, that's energetically favorable. So when determining a good leaving group, remember, the first thing you do is you imagine it as an acid, and you see, is it a strong acid creating a stable conjugate base? And what are the things that determine a stable conjugate base? Well, if it's a large conjugate base, then that charge is spread out over a larger atom, and also the electronegativity of the atom. If it's a very electronegative atom, then it likes dealing with that negative charge, so it will probably be a pretty stable conjugate base, and therefore a pretty stable leaving group.